Good morning, and welcome to our first talk, which is first in an occasional series of public talks that we're going to be broadcasting using our conferencing system here at the virtual NASA Lunar Science Institute. We're also going to be streaming this via YouTube. I'd like to first say thanks to everyone out here who has come to help us do a stress test on this conference system that we have. We are preparing for the first all virtual NASA Lunar Science Forum, which is taking place in just a few weeks. All of you out there in the Twitterverse are going to be hearing about that, and we hope you're able to join us via the YouTube stream. So thanks again for helping us stress this system. My name, again, is Greg Schmidt. I'm the Deputy Director of the NASA Lunar Science Institute. We're about to change our name to the Solar System Exploration Research Virtual Institute and expand our focus from not just the moon, but also include asteroids and the moons of Mars as well. But for now, we are focusing only on the moon, and we're really excited to share with you some of the upcoming mission highlights that Brian Day is going to be talking about in just a minute here. Brian is our Director of Communication and Citizen Science, and he also, I want to give him and his team a little bit of a congratulations for a successful launch of the IRIS mission just last night. I suspect many of you heard about this on the news media. Very exciting, launched via a Pegasus airdrop. So and so far 100% successful. So we're very excited about that. So without further ado, Brian, take it away.
Thank you very much, and thank you all for joining us here today. This is a very exciting time. This is a very exciting time to be studying the moon. A new generation of robotic lunar explorers is completely revolutionizing our understanding of the moon. The previous view we had of the moon of a static, completely arid, completely airless environment is being replaced by a world with a very dynamic environment. Some of this realization came about from the understanding that at the poles of the moon, the sunlight comes in at a very shallow angle, and because the pole of the moon has a tilt that results in essentially no seasons, that means that craters at the poles of the moon have floors that are permanently shadowed. As the sunlight comes in, the rims around those craters create shadows, and there are craters at the poles of the moon whose floors have not seen sunlight in over 1 billion years. People started realizing that if water ice was going to accumulate anywhere on the moon, this would be an excellent place to look. We got our first evidence for this from 2 probes back in the 1990s, Clementine and Lunar Prospector, and they both provided preliminary evidence that there might be water ice in these areas. Clementine utilized a technique called bistatic radar imagery. And as Clementine flew above the surface of the moon, it bounced a radar beam off the surface of the moon. An interesting thing happened, though. It turned out that as that beam reflected off the surface, it came back polarized in a way that was consistent with that beam having passed through crystals of water ice. Now, this only happened right near the poles of the moon. And so about half the people who looked at that data said, wow, look at that. That looks like water ice. But the other half of the people who looked at it said, no, we're not convinced, because a very rough surface could give a similar signature. However, again, it was really interesting to note that that only happened right in the vicinity of the poles. So it was kind of hard to say, why would you only have a rough surface like that right in the polar area? It seemed to make sense that ice would be the source for that signature. So a follow-up study was done with the high-resolution Arecibo radio telescope in Puerto Rico. And that further clouded the issue because under the high resolution from Arecibo, it became clear that the areas of high circular polarization ratio did not exactly correspond with the shadows. And so if this was coming from ice, it was hard to really justify how that ice would exist outside the shadows. So the debate continued. In 1999, we got further evidence from the Lunar Prospector probe. Now, Lunar Prospector had on board a neutron spectrometer, and neutron spectrometers are very, very good at detecting the presence of hydrogen. However, they're very bad at telling you what form that hydrogen takes. Is it just hydrogen in and of itself? Is it part of a compound? It doesn't tell you that. But Lunar Prospector did find anomalously high concentrations of hydrogen at both the poles of the moon. Now, we didn't think that that was going to be just hydrogen in and of itself, because that probably wouldn't remain resident on the moon very long. So it was most likely in the form of some compound, and one of the most common compounds out there is H2O. But it's important to note that Lunar Prospector couldn't actually tell us, yes, it's water. It could just say there is hydrogen there. So at the end of the Lunar Prospector mission, it was decided, well, let's try and figure this out. So Lunar Prospector, at the end of its mission, was directed to impact at the south pole of the moon in an attempt to generate a plume that could be studied from here on Earth. And we would therefore be able to look for spectral signatures of water. The problem with this is that Lunar Prospector was a very light spacecraft, only 161 kilograms. And because it was in orbit around the moon, it wasn't moving very fast. And at the end of its mission, as it was deorbited, that meant that the orbit just got smaller and smaller in radius. So as it came in at a very low angle, just kind of skittering across the surface, only 6.3 degrees. So it came in low, slow, and shallow. As a result, there was no plume developed, and the results were inconclusive. But it was an interesting idea. So fast forward now to 2009. We have two spacecraft, the Lunar Reconnaissance Orbiter, or LRO, and the Lunar Crater Observation and Sensing Satellite, or LCROSS. Both of these spacecraft launched together, and part of their goal was to try to answer this question if in fact there was water ice at the poles of the moon. They launched together on an Atlas V rocket from Cape Canaveral on June 18, 2009. We'll talk about LCROSS first. Its goal was to excavate one of these permanently shadowed craters at the south pole of the moon. LCROSS carried with it the upper stage of our Atlas V rocket, the Centaur upper stage, with a mass of about 2 tons, something about the size of a school bus, but with a velocity of 2.5 kilometers per second, 5,600 miles an hour. As LCROSS approached the moon, it carefully aimed and targeted that Centaur upper stage toward the floor of one of those permanently shadowed craters, released it, and sent it flying down into that crater, again at 5,600 miles an hour. The impact excavated several hundred tons of material, sent it flying up out of the shadows into the sunlight, high into the sky of the moon, where then the little robotic LCROSS spacecraft flew through the cloud of debris, sensing it, looking for signatures of water ice. This is a picture taken from the LCROSS spacecraft looking into the permanently shadowed region of the crater Cabeus near the south pole of the moon. And in that dark shadow, you can see a small point of light. That is the actual thermal flash from the Centaur hitting the ground. If you look carefully in this picture here, you can see a small white patch now amongst the shadow. That is the cloud of material rising up off the surface of the moon. And here we have data from the LCROSS spacecraft. The red line represents a reference spectrum for water. The black dots are the actual data from LCROSS. Now, everywhere you have a dip in that red reference spectrum line, that represents an absorption feature, a fingerprint for the H2O molecule. And if you'll look closely, you'll see that wherever there's a dip in that reference spectrum, you'll also see a dip in the LCROSS data. This shows that we did indeed detect water vapor on the moon. Now you'll notice that there's also some additional dips in the LCROSS data. That's showing that, in fact, we found a lot more stuff there sequestered in these dark shadows. As a matter of fact, people will be going through this data for years, seeing what all was excavated. For many years. Flying along with LCROSS was the Lunar Reconnaissance Orbiter. And LRO is still in orbit around the moon right now, creating a comprehensive atlas of the moon. Aboard LRO are a very high resolution camera, a laser altimeter that measures all the ups and downs of the surface of the moon, a means of peering into these permanently shadowed areas. It's kind of like a very sophisticated night vision instrument. LRO is also characterizing the radiation environment of the moon and the thermal environment of the moon, and it's sniffing out these deposits of hydrogen where we now know water is sequestered. One of the surprises that came out of LRO was when we looked at the temperatures of these permanently shadowed areas. We expected them to be cold, but LRO has found the temperatures to get down to 25 Kelvin. This is the coldest temperature we have yet measured anywhere in our solar system, even colder than what we've measured so far on the daytime side of Pluto. So this is the coldest area that we have measured anywhere in the solar system, and it's right next door. Obviously, a good place to look for volatiles. LRO is also telling us a wonderful story of the impact history of the surface of the moon. The moon is covered by craters that are the result of billions of years of meteoroid and comet impacts. The same thing has happened here on Earth, but here on Earth, because of plate tectonics and because of erosion, that history has been erased from the surface of the Earth. But because there's so little erosion on the moon, because there's no plate tectonics on the moon, that history is very well preserved. And so we can understand the history of impacts in the inner solar system, and also therefore understand better the environment here on Earth during the early days of the solar system. We now realize that the early solar system was indeed a very violent place, and it is quite likely that life had to arise on multiple occasions here on Earth before global extinction events from impacts reset the clock and things had to start over again. One of the very fascinating things that we are also learning from LRO is that the water ice that we find at the poles is not necessarily confined to those permanently shadowed craters. Even outside the permanent shadows, the sunlight, as it comes in, is coming in at such a low angle that it does a very poor job of heating up the ground. And so, therefore, just beneath the surface, you could have deposits of permafrost. From a utilitarian point of view, this is important because if you're going to try and harvest water ice, it's nice to not have to go into a 25 Kelvin cold trap. This also could provide some insights into the information we got from the Arecibo telescope years before, when we noticed that there wasn't this coincidence between the permanent shadows and the polarization signatures. Perhaps this is telling us why. Another interesting fact is even away from the poles, at low latitudes, we're finding that there is water on the moon. 3 probes, the Chandrayaan probe, NASA's Deep Impact, and the Cassini mission, all detected through infrared spectrometry a thin veneer of water molecules in the soil of the moon, even away from the poles. This was a surprise. Where would all this water come from? We have several good candidates. One is comets. Comets have been bombarding the moon for billions of years, and they consist of large amounts of water. Imagine when a comet hits, a vapor cloud going up. Much of that water may be lost to space, but some of it, as it spreads across the moon, will encounter cold traps and will condense in those permanently shadowed craters. Another source could be the sun itself. The sun sends out a solar wind, a wind of high-velocity hydrogen atoms. And as these hydrogen atoms cross space at high speeds and they impact the moon, they could interact with oxygen atoms in the silicates of the lunar minerals. And perhaps water is actually being manufactured through this process on the surface of the moon. But one thing we felt fairly certain of was that this water was not native to the moon. It came from outside sources. And our feeling about that came about from our understanding of how the Earth and Moon formed. We have good evidence that the Earth and Moon formed together in a giant collision about 4.5 billion years ago. There's reason to believe that perhaps a planet about the size of the Earth and a planet about the size of Mars collided. The heavy nickel ion cores of both those worlds sunk together to form the large nickel ion core that we have now, and some of the lighter silicate materials from the impact were blasted off into space. Some of that was lost into space, but a fair amount formed a disk around the early Earth. And then the moon accreted from the material in that disk. But because that was such a high temperature event, the volatiles would have been driven off, and this material that the moon formed from would have been very, very dry. At least that was the theory until quite recently. The Apollo 17 astronauts brought back with them samples of material called orange soil. And this orange soil consists of actually beads of volcanic glass that were erupted in a fire fountain long ago. Now, if you do an analysis of those beads of volcanic glass, you find that, in fact, they are very dry. The water content is quite low. But that's not real surprising. If you're doing an eruption in essentially a vacuum, you would expect to see outgassing of water, such as into space, water and a variety of volatiles. But inside many of these beads are little crystalline cases, lunar melt inclusions, crystalline olivine structures that formed beneath the surface of the moon before this material was erupted. And they encased magma from deep beneath the surface of the moon. And that magma being encased in these structures was protected from outgassing during the eruption. Recently, the techniques using ion microprobes were developed to actually sample the magma that was encased inside these structures. And surprisingly, it was found that the water content of that magma was about the same as water or as magma here on Earth that is erupted at the mid-oceanic ridges. That was a surprise. As we mentioned before, there is a wonderful camera on board LRO that is giving us fantastically detailed pictures of the lunar surface. We see volcanoes, such as the grutois and domes here. We see a feature here that appears to be a dry riverbed, but no water ever flowed here. This is a sinuous rill, and through this channel long ago, molten lava flowed. This is actually the Hadley Rill, which was visited by the astronauts of Apollo 15. We, of course, see craters across the surface of the moon, but we see some other interesting holes on the surface of the moon, lunar pits, and these holes seem to open up into vast voids beneath the surface of the moon. What many are thinking is that these may be skylights opening into subterranean lava tubes. I mentioned that the camera is really good. This is a shot here of the Apollo 14 landing site. On the right-hand side of the picture, you can see the descent stage of the lunar module. This is what the astronauts rode down to the surface of the moon upon. On the left-hand side, you can see a little white dot that is being pointed to by an arrow there. That is an instrument package that was left behind by the Apollo astronauts. If you look very carefully between the descent stage and the instrument package, you can see a series of dark squiggly lines. These are actually the footprints of the astronauts. Again, it's an excellent, excellent camera. Now you can help explore the moon. We have a variety of programs out there that will allow you to actually receive images from LRO. I would point out Moon Mappers and MoonZoo. A new addition to this is the Lunar Mapping and Modeling Portal. This gives you access to a wide range of images and data from both LRO and a variety of previous missions. And very soon, you will actually be able to receive this information on your smartphone. It's an outstanding way to conduct your own exploration of the surface of the moon. Now, as we look across the surface of the moon, we also see a series of curving cliff faces called globate scarps. And these seem to tell an interesting story of the early history of the moon. These tell a story of how the moon has actually shrunk as it cooled. The early moon was quite warm, but as it cooled and shrunk, the rigid surface of the moon would actually buckle. And the initial view of these globate scarps was quite interesting in that it appeared to tell us something about the very earliest days of the moon. But as the high-resolution cameras of LRO zoom in on this, we see something fascinating. We see small, relatively well-preserved looking craters actually being overridden by the face of these scarps. This means that this scarp face in this position has to be younger than those craters that it is overriding. This is a much more recent phenomena than we had previously realized. And many now believe that this process is still going on today. Now, when I was in school, I learned that the moon was essentially geologically dead. This contradicts that. And we get further evidence looking at the seismic data from the moon. Now, when we sent the Apollo astronauts to the moon, we expected them to encounter moonquakes. We expected that there would be moonquakes caused by meteoroids slamming into the surface of the moon. We expected that there would be moonquakes, deep moonquakes, caused by the tidal stretching of the moon by Earth's gravity. We've anticipated that there might be moonquakes caused by thermal expansion and contraction of surface rock, as that rock went from the very hot daytime side of the moon to the very cold nighttime. And as a matter of fact, the seismometers left behind by the Apollo astronauts detected all three of those types of moonquakes. But there's a fourth type of moonquake that was also discovered, something that wasn't expected. These moonquakes occur at depths of 20 to 30 kilometers beneath the surface. They get up to magnitude 5.5 and can last for over 10 minutes. Let me assure you right here and now that if you are in a magnitude 5.5 earthquake that is lasting for more than 10 minutes, you will quickly conclude that the object you are sitting on is not geologically dead. What is causing these moonquakes? We don't know. But we're getting some clues. Clues from a mission called GRAIL, the Gravity Recovery and Interior Laboratory. And GRAIL consisted of two spacecraft flying in close formation together. And just as LRO is mapping the surface of the moon, GRAIL, using gravity mapping, was able to map the interior of the moon. Here we see a gravity map from GRAIL. And one of the things that we are learning from this data is that, as a matter of fact, the moon's crust is significantly thinner than we had previously thought. GRAIL is telling us that the crust is 34 to 43 kilometers thick, which is about 10 to 20 kilometers thinner than we had previously believed. We also see the crust as being very highly fractured. We can also now understand how certain impacts would allow denser material from the mantle to well up into the crustal region and form the mass cons that spacecraft now encounter as they orbit around the moon. Another pair of spacecraft in orbit around the moon are the Artemis probes. And the Artemis probes are studying how the solar wind streaming out from the sun interacts with the surface of the moon. One of the things that we've found is that the solar wind actually blows material off the moon into a comet-like tail. And this tail is actually quite long. It is much longer than the separation between the moon and the Earth. This means that as the moon goes around the Earth, once a month the Earth actually passes through that tail of debris. Similarly, the Earth's outer atmosphere is blown into a comet-like tail. And once a month, the moon passes through that tail of the Earth's atmosphere. So we are not quite as isolated from each other as we had once thought. This also could give us some clues as to the formation of the lunar atmosphere. Now that's a loaded term right there, because again, when I was in school, I learned that the moon does not have an atmosphere. But in fact, the moon does have an atmosphere. It's very thin. Here on the surface of the Earth, if you take a cubic centimeter of atmosphere, you would find about 10 to the 19th molecules within that cubic centimeter. If you were to do the same exercise on the surface of the moon, your sample would include about 100,000 to a few million molecules. Now that sounds like a lot, but it's actually an excellent vacuum. And as a matter of fact, the atmosphere on the surface of the moon is roughly of the same order of what our astronauts experience in the outermost fringes of the Earth's atmosphere when they do a spacewalk at the International Space Station. What's the moon's atmosphere made of? Well, we don't know. It glows most brightly in the light of sodium, but that's probably a minor component of the lunar atmosphere. Technically, the moon's atmosphere is considered a surface boundary exosphere. Basically, that means it's a very thin atmosphere. Here on the surface of the Earth, the motions of molecules are dominated by collisions between those molecules. But the atmosphere of the surface of the moon is rarefied enough that it's essentially a collisionless environment, and molecules are free to carry out ballistic paths. We also believe that there may be an active dust component to the lunar atmosphere. We got our first clues from this from the robotic surveyor probes, landers that landed on the surface of the moon, and this was before Apollo. Looking out at the horizon, when the sun would be just below the horizon, they detected glows above the horizon. Now, if the lunar sky was empty, you would not expect to see a glow such as this because there's nothing there to reflect the light of the sun beneath the horizon. But on multiple occasions, these glows were detected. What was thought was that perhaps dust was somehow being levitated above the surface of the moon, catching the sunlight and reflecting it into the camera of Surveyor. We got support for this idea from the subsequent Apollo missions, and on several occasions, astronauts in the command module orbiting around the moon would look out the window of the command module, and again, with the sun just below the horizon, would see beautiful jets and streamers heading up into the sky, even up to the altitudes at which they were orbiting. The thought was perhaps dust was being electrostatically levitated off the surface of the moon and into the sky. Further support for this idea came from an instrument that was left behind by the Apollo 17 astronauts. It was designed to look for micrometeoroid impacts. And one of the interesting things that this instrument found was that twice every lunar day, there would be very sudden peaks of very, very many, very, very small impacts. And these peaks happened right at lunar sunrise and right at lunar sunset. Now, the energy environment between the dark nighttime side of the moon and the bright daytime side of the moon is such that you can expect to see very different charges on the surface. And so what this has been interpreted as indicating is, again, the electrostatic transport of dust across the terminator, across this line between day and night. So the lunar environment turns out to be a very complex place. The atmosphere of the moon has multiple sources, solar photons and energetic particles, the hydrogen coming from the solar wind. You have meteoroid impacts. Those can result in vaporization of the meteoroids and vaporization of native rock. You have interior outgassing. You have chemical processes. And you have this very different electrical charge environment between the daytime and nighttime side of the moon. So imagine a day in the life of a water molecule on the surface of the moon, and it would just actually sit on the surface until some energetic event, either a meteoroid impact or a photon or a high energy particle, gives it energy. And if there's sufficient energy, it'll escape into space. Otherwise, it will just carry out a ballistic parabolic course up into the sky and then landing back down on the surface, waiting for the next energetic event to cause it to leap again. And so through a series of random hops, it moves across the surface of the moon. Eventually, it may make it to the poles and encounter one of those cold traps where it freezes out into a deposit of ice. But even in those cold traps, there can be very intense radiation. And some of that radiation may actually sputter some of the ice off the deposit, or the water off some of the deposit of ice, where it again becomes part of the lunar atmosphere and can again cycle across the surface. So what we may be seeing here is actually the atmosphere mediating a lunar water cycle. That's a phrase I never would have dreamt of saying 5 years ago. Why do we care about all of this? Well, it turns out this type of atmosphere that the moon has, a surface boundary exosphere, is actually probably the most common type of atmosphere in our solar system. Our atmosphere is an exception. But this type of atmosphere, surface boundary exosphere, Mercury has one, the moon has one, many of the larger asteroids, a number of the moons of the giant planets, even some of the distant Kuiper belt objects, icy worlds out beyond Neptune. This is the most common type of atmosphere in our solar system, and we know next to nothing about it. But we happen to have one in our own backyard. How lucky is that? And so we're planning to explore it with a new probe, LADEE, the Lunar Atmosphere and Dust Environment Explorer. LADEE is going to go into orbit around the moon and then dip down low, actually flying through the lunar atmosphere, sampling it, letting us know what it's made of, what its structure is, and how this changes over time. It'll also look for lofted lunar dust. The important thing is the time to do this is now, because a number of countries, the United States and a number of others, have plans to send missions to the moon, many of them robotic, but some even carrying humans. And all that activity on the moon, thrusters firing, people exhaling, all of that could quickly overwhelm this very thin, fragile atmosphere of the moon. So the goal is to explore and understand the lunar atmosphere before we change it. LADEE will carry 3 scientific instruments on board, a mass spectrometer, an ultraviolet spectrometer, and a dust detector. It will also carry a technology demonstrator, the Lunar Laser Communications Demonstration, that will test the idea of using a laser instead of radio waves for communicating, and by doing so, bring broadband speeds to the moon. This is a diagram of the spacecraft configuration. LADEE stands about 2 meters tall, about as tall as I am. It has a mass of about 330 kilograms, again, about like me. It is actually a small spacecraft, but we like to say big science with a small spacecraft. Here you can see a picture of LADEE going through the integration process at NASA Ames Research Center. It has since left NASA Ames, heading toward its launch site for a launch this coming September. It will be the first deep space launch from NASA's Wallops Flight Facility in Virginia. This will also be the first mission to fly on the brand new Minotaur 5 rocket. LADEE will go into orbit around the moon, a retrograde near equatorial orbit, and conduct a 100-day science mission studying the lunar atmosphere. A note on the Minotaur 5 launch vehicle. This is from Orbital Sciences Corporation. It's a 5-stage vehicle, all 5 stages being solid rocket propellant. The Minotaur 5 uses engines that were essentially recycled from the old Peacekeeper MX missiles. And under agreement with the then Soviet Union, these missiles were scheduled for destruction. But the engines, which had to be destroyed, well, you can get somewhat creative in how you destroy these engines. And one way of doing that is to use them, well, to send a payload to, say, the moon. So this is an excellent example of swords into plowshares. Let's see, yeah. Now, this is going to be a very exciting mission, but it's something that we don't expect you to just watch us do. It's something that you can participate in. In particular, amateur astronomers can play a very key role in this mission. Again, we believe that meteoroid impacts may be one of the primary sources for the lunar atmosphere. And it turns out flashes from meteoroid impacts are ideally detected with telescopes with diameters of 8 to 14 inches. That's the size of telescope that many amateur astronomers and local schools will have. And so we're asking these people to participate in the science of the mission. What we would love to have happen is as many eyes as possible be watching the moon during the course of the LADEE mission and watch for the flashes of meteoroid impacts so that we can compare any changes that our instruments see in the structure and composition of the lunar atmosphere with these impacts that are detected from here on Earth. So again, if you would like to participate, we invite you to join us. Go to the LADEE mission page, and you can go to www.nasa.gov/LADEE, L-A-D-E-E, and follow the link there for how you can get involved. Now, this is all great if you happen to have an 8 to 14-inch telescope. And if you do, here's an example of what you can see. If you take a look in this loop, you will see at the top the bright sunlit section of the moon, and below that you see the darker nighttime side of the moon. And in the lower right, if you look very carefully, you'll see a flash occurring along the limb. That's something about the size of a walnut, a meteoroid slamming into the surface of the moon. So again, an 8 to 14-inch telescope equipped with a very simple, inexpensive video camera can obtain results such as this. This will be very valuable to the mission. That's fine if you have an 8 to 14-inch telescope, but a lot of people out there don't. But they can still participate, because it turns out the majority of the impactors hitting the moon are very, very small, only about the size of a micron in diameter. And we would never be able to see the flash of an impactor that size from the distance of here on Earth. But it turns out, since the Earth and Moon travel together through space, they encounter these streams of debris together. And even a very small impactor, when it encounters the Earth's atmosphere, can become very evident in the form of a meteor. When you look up in the nighttime sky and you see the typical meteor in the sky, that is caused by a solid object only about the size of a grain of sand. So what we would love to have happen during the course of the during the course of the LADEE mission is to have as many people as possible go out and do meteor counting. The beautiful thing about counting meteors is that there's virtually no equipment requirement at all. You don't need a telescope. You don't need binoculars. I do recommend a reclining lawn chair. You might as well be comfortable. But again, because the Earth and Moon are traveling together through space, as you make your counts of meteors, we will then be able to make inferences as to what's happening on the surface of the Moon at that time. And as is the case with almost everything these days, there's even an app for that. So NASA's Meteoroid Environment Office has come out with Meteor Counter. The Meteor Counter runs on your iPhone or your Android phone. And the beautiful thing about your smartphone is that it knows where you are and it knows what time it is. So as you go out under the nighttime sky, you simply look up in the sky, and when you see a meteor, you tap on your screen. You tap on the right-hand side for a bright meteor, the left-hand side for a dim meteor, in between for an in-between meteor. And this app will record your observation along with where you were and what time it was. At the end of your observing session, it will send that information to NASA. So anyone can become part of the science team for the LADEE mission. Also, if you happen to be an amateur radio enthusiast, there's a unique opportunity for you to participate here, because it turns out that many of the meteors that we encounter are not visible. There are a number of meteor showers that the Earth and Moon experience that come in from the daytime direction, and we'd never be able to look up in the sky and see them. But as many radio amateurs have already learned, they can hear these meteors coming in. Radio amateurs routinely make use of that to be able to do very distant communications, bouncing radio signals off the ionized columns of gas that these meteors produce. So again, what we would love to have happen is radio amateurs making counts of meteors that they detect. So again, we invite you to become a part of our exploration of the Moon. There's ample opportunity, and we look forward to exploring the Moon with you.
Thank you very much, Ryan. So we would be happy to take questions from our online audience right now. You can do this through the chat function if you're on Adobe Connect. So we will hang out here and wait for a few minutes if there's any questions, which we invite. And let me say again that this is only the first in an occasional series of public talks. We hope to reach out to quite a wide audience and share the pretty cool things that are going on with the Moon, and then with asteroids and the moons of Mars as well. So thanks everyone for coming and listening to this.
So one of the questions I'm seeing right off the bat was a question about the data rate coming from the LLCD, the Lunar Laser Communications Demonstration. And we're looking at up to 622 megabits per second. That is a dramatic improvement over what we would get with the medium gain antenna aboard spacecraft such as LADEE. One of the things that happens in planetary explorations is you find that because of mass constraints, your transmitters and your antennas tend to be very small, and the output tends to be very small. And when you start getting to large distances, that means your data rates become very, very low. So the idea of being able to get over 600 megabits per second, possibly, at a distance of the Moon is very, very exciting indeed. Now, in the case of the LADEE mission, this is a technology demonstration, so it is actually separated from the scientific instruments aboard LADEE. So we will not be actually transmitting the scientific data from LADEE via the LLCD. Instead, there will be test data that is being sent from the LLCD. But in the case of LADEE, we will not be actually using this for our data from our scientific instruments. But we can look forward to that in the future.
So we have another question from Megan online. So the public has telescope monitoring, iPhone app, and amateur radio monitoring. Did I miss anything? Meteor counting?
Yeah, so we again have, so the telescope monitoring, you're right, in terms of looking for the meteoroid impacts, counting meteors. Another way that people can participate is by going to moonzoo.org or Moon Mappers. And these are programs that allow you to help with our exploration of the surface of the moon. There are several programs that these entail. One is to actually do crater counting. As we look at the surface of the moon, we can compare relative ages of different surfaces by counting the frequency of craters. The older a piece of real estate on the moon, the more craters it's going to have. We can also look for fresh impact craters. And one of the interesting programs that's going on right now is a comparison of the newer imagery from the Lunar Reconnaissance Orbiter with the imagery from a few decades ago from the lunar orbiters. And we have these two sets of maps of the lunar surface. And already people have started discovering craters that appear in the Lunar Reconnaissance Orbiter data set that were not there back in the 60s from the Lunar Orbiter data set. So we're discovering craters that are brand new. Something else that people are using the LRO data for are to look for some of the previous probes that have gone to the moon. A number of the early probes that have gone to the moon have not been located yet. And so there is an active program now of searching through these high-resolution images, looking for some of these early pioneering efforts to the moon. Another thing that people are doing are looking at the relative apparent frequency of boulders and the excavation of material, more solid material from impacts, digging up these more solid pieces of rock out of the more, if you will, fluffy regolith. So the ability to excavate some of this really interesting deeper material. The Association of Lunar and Planetary Observers has a very active lunar observation section. I would again refer you to work with the ALPO. There are a number of really outstanding lunar programs there. And we are happy to be partnering with the ALPO in our impact observation campaign.
One thing I'd like to mention as well as a quick aside here is that the person who started our citizen science program here at the NASA Lunar Science Institute was the Nobel Prize winner and founding director of the NASA Astrobiology Institute, Baruch Blumberg. Our building here that the NASA Lunar Science Institute is headquartered in is actually named after him. He passed away about 2 years ago, but he had great enthusiasm for bringing as many opportunities to the public as possible. And I think it's really kind of an honor that we can be following in those rather big footsteps.
Very much.
Yeah. So we have a question on someone who wants to get engaged on Facebook with what we do here and space exploration, and we do have a Facebook page. It's NASA_lunar. Let me ask one of our tech people, Ashkan Nejad here, if he has any suggestions for how to join. I think you can just follow it. Is that correct? Yeah. Yeah.
Also, I'll point out that there will be an active social media component to the LADEE mission. There will be a NASA social at the launch event. We'll also be having a series of social media ambassadors. So if you would like to get involved, I would refer you to the moon.nasa.gov website. And if you go there, look for the LADEE launch events link, and you can learn how to participate in the social media aspect of the LADEE mission. I also see that there was a question asking about lunar transient phenomena not associated with meteoroid impacts, but rather as a result from internal activity on the moon. And yes, we know that some of the lunar atmosphere, especially when we look at certain components such as argon, do come from internal outgassing. Now, we will not, on LADEE, be able to specifically detect these types of LTPs that are possibly a result of outgassing, but amateur astronomers, the Royal Astronomical Society, the Association of Lunar Planetary Observers, there are active programs looking for these types of events. And people have been doing this for years. Again, what we would love to have happen is for people to be watching for these types of events during the course of the LADEE mission. So pay special attention during the LADEE mission, because if there is such a transient phenomena observed, then it would be very, very interesting to try to correlate that event with any changes in the composition and structure of the lunar atmosphere that LADEE's instruments see. So yes, please, please do keep your eyes and telescopes going.
I'd like to do a special shout out for Marchese online, who has submitted a few questions from Italy, and we're very happy to have you online. And what I want to emphasize here is that although we are an institute that's funded by NASA, we fund our 7 domestic teams. We're about to do a selection of some new domestic teams. We also really consider ourselves an international institute. We have 7 existing international partners. There's a hub of activity in Europe, Canada, in the Middle East, and Korea, and this is growing. And we just think this is so exciting. The exploration of space, and in particular the moon, is a very different thing than it was 40 years or so ago, when it was really just the United States and the then Soviet Union. There's a lot of people, a lot of countries around the world who are now joining us, and what you need to do to explore space, particularly with the CubeSats and other similar satellites, has gone down so that the access is in the hands of oftentimes college students. And I think that we at NLSI here rejoice in that. We're very excited about that, and we want to lift up the whole world and to join us in the exploration of the moon, asteroids, and the moons of Mars. So I'm not seeing any more questions at this point. So I think that I would like to again thank Brian for another wonderful talk. So
thank you very much.
Yeah, and thank you so much to everyone online for joining us. Please just continue following our Twitter account and Facebook, and you'll be hearing about other opportunities in the near future, particularly the Lunar Science Forum coming up in just about 3 weeks. So thanks again. Bye-bye, everyone.